So we want to talk about gravitational potential energy on a big scale, so on a planetary scale. And so this is a person floating in space near a planet. The person has a mass and the planet has a mass. Let's call this planet by some phonetically appropriate name. Something that sounds good to the ear. Earth. Okay? So this person's floating near Earth and feeling force due to gravity. Of course, people talk about not feeling any force due to gravity in space. They're trying to talk about not feeling, or about feeling weightless in space. You just can't feel it. You don't have maybe a normal force against anything to push, so you're not going to feel that feel any pressure against the surface. But really, there is a force due to gravity according to Newton's universal law of gravitation. And it's described using the force due to gravity equation that we discussed earlier. Fg is equal to g m1 m2 over r squared. But using a little bit of calculus, now it's really not a part of this course to discuss how we go from one to another, but you can notice the similarity in structure at any rate. The gravitational potential energy on such a scale, I'm going to call it E big G because it's got big G in the calculation, the universal law of gravitation, is g m1 m2 over r, not r squared. And it's actually negative g m1 m2 over r. So I want to set up this problem with some givens. Let's make the mass of the person, I'll make P stand for person, equal to 60.0 kilograms. And since this is Earth, I'm going to say that it's 5.98 times 10 to the power of 24 kilograms for the mass of our planet. And the radius of Earth is 6.40 times 10 to the power of 6 meters. So pretty big planet. Now, what I want to point out that a lot of people, on first inspection don't catch is that radius is the radius of our planet, the average radius of our planet. This orange label over here, is that the radius of our planet? No, that's the radius from the center of the Earth out to the person that's floating in space. What we've been told with R sub E is that value. So we need to know an additional piece of information, and that's the person's altitude. So I'll label it as alt for altitude, and I'll label this as the radius of Earth. So the extra piece of information would be, well, I'll put it into the question that I'm going to write down here in just a moment. At an altitude of 20,000.0 meters, find the daredevil's EG. Okay, and I'm just calling this a daredevil because this person could potentially fall to Earth from this extreme height. Okay, and we've seen this happen recently in the news. So from 20 kilometers up, this person could fall. Okay, and rather than talk about roller coasters, let's just drop somebody out of a spaceship from 20,000 meters up. Okay, why not? So before we do anything like drop them out of a spaceship from 20 kilometers up, we got to find EG. So let's plug in some values. I'm going to do it up here. Although you should do it further down on your page so the layout is nicer, but I'd like to keep it all on one page. So I'm going to say EG is equal to negative 6.67 times 10 to the power of negative 11. And for lack of space, I'm going to drop the units, but of course you should always write your units. I just have a great big fat marker here. 6.67 times 10 to the power of negative 11 times the mass of the person, which is 60 kilograms, times the mass of the planet, which is 5.98 times 10 to the power of 24 kilograms, all divided by the radius. Now the temptation here is to throw in the radius of the Earth, but remember, we know it's not just the radius of the Earth. We know that it's the radius of the Earth plus the altitude. So we've got to include that. And the radius of the Earth is 6.40 times 10 to the power of 6 plus the radius of plus the altitude, which is 20,000 meters. Yeah, G is a constant, 6.67 times 10 to the negative 11.
Gotcha.
Universal gravitational
What is the
Newton meters squared per kilogram squared.
Oh.
Yeah, I'm just dropping the units because my marker's too fat to fit
Yeah.
them. It is certainly bad form. Okay, and I need your help with the calculations though. You just need to keep the denominator in brackets, otherwise it gets messed up. Very important that denominator stays in the brackets. And it will be a negative value, but that's okay. We only care about the absolute magnitude. Yeah?
I don't care about the absolute magnitude. Why?
Well, the negative sign is going to be important in a minute.
Okay.
Don't worry. It's not for no reason.
Okay.
They'll come up. Anybody got an EG for me? It's a lot of scientific notation. Ali.
Negative 3.73 times 10 to the 11.
Can you give it as many decimal places as you can?
Oh, okay. 3.72,
Points.
sorry, 277, 1962.
6, 2 times 10.
To the
14?
Yes, I swear to God, we helped you.
All right. Joules. All right, so we've got a gravitational potential energy of so many joules, okay? A lot of energy. Because this person is going to fall. So that's the next part of my question. I'd like to ask the question, part II.
Yeah.
If she falls,
Oh, why did I put Newton? It's Joules.
did I call this daredevil a he?
Yeah.
Oh, no, let's make this equal opportunity. I mean, ladies can do crazy things too.
Exactly.
She's going to fall from this great height. If she falls to the earth, from a stationary start, what will her impact speed be?
That's gonna be fast.
Now we're going to neglect air resistance here, as we often do. So clearly, whatever result we get here is going to be a little bit higher than it should be, because this lady is going to crash through the atmosphere. Yeah, a lot higher. But suspend your disbelief. Okay, we're not going to talk about the drag forces just now, because it does complicate things substantially. We're just talking about conservation of energy in the absence of air resistance. All right, so let's talk about how to calculate this value. I want to pull in another sheet of paper here. So in our situation, we've got our planet Earth, and we start with this lady floating in space out here. Oh no! And then somehow she gets released and she's crashing towards the planet. Oh no! And here's the radius of Earth. Now what we're going to need to do is calculate what her EG is. I'm going to say at position B. We've already calculated what her EG is at position A. And if we're going to get to her kinetic energy, which will let us get the final speed, I want to lay this out. So E total at position A should be equal to E total at position B, assuming that this is a 100% efficient drop, no energy lost to air resistance or friction. So I could say EKA plus EGA equal to EKB plus EGB. No problem. Now at the top, EKA is equal to 0. But I can't say that at the bottom EGB is equal to 0 because she's still a certain distance away from the center of the Earth. Everybody got that so far? Okay. So I got to get EKB all by itself because that will let me get to the speed of this lady. So EKB will be equal to EGA minus EGB. So I'll ask you to calculate what EGB is. And off to the side, I'll show you how to set it up. What we calculated before was EGA. So we'll borrow that in just a second. But now we have to calculate EGB, which will be GMP, mass of the person, times mass of the Earth, divided by, now it's not the radius of the Earth plus the altitude, now it's just the radius of the Earth.
Isn't it negative?
Oh, and negative, I'm so sorry, yes. As soon as you've got the EGB, let me know what you've got. Yeah?
For EG, like the first one, you got it. It was times 10 to the 31, right?
Times 10 to the 14.
Why do I have to the exact same numbers, but to the
There might be an issue with your scientific notation. Did you get it already?
Yeah.
Okay.
Negative 3.739368.
Oh, say it again. Negative.
3,
Yeah.
7393685 times 10 to the 14.
Times 10 to the power of 14.
What is mine? That's not showing up.
Okay, so we've got an EGA and an EGB. So now I want to expand it out. I want to write it in full. EKB should be equal to EGA minus EGB, and EGA was negative 3.72. Of course, you can keep this in your calculator's memory, so it could be easier for you. 3.72771962 times 10 to the power of 14 joules minus negative 3.73936875 times 10 to the power of 14 joules. And what do you get for EKB? Has anybody got their subtraction? It's still going to be a big number. Yeah. I mean, they look similar, but it's still a big number. Because it's 10 to the power of 14. Yeah? But they're only different on the third decimal, on the third digit.
It's still not showing.
Anybody get the difference between the two values? Yes?
1.1649
1.1649, yeah.
15 times 10 to the 12.
Times 10 to the power of 12 joules. All right. So now we want to figure out how fast this person is going. So EKB is equal to 1/2 m of the person times v, position B squared. So VB, if I do a little bit of rearrangement, should be equal to 2 EKB over MP, all square rooted. And so I'm not going to rewrite that big number, but can I ask you to please do 2 times that energy value divided by the mass, all square rooted. And it will be a big number, I know that. It might even be an unrealistic number. Anybody get it? What happened to Alex today? Alex is usually so all over this stuff.
My calculator just is not getting these numbers right.
Oh, really? Okay.
Like, I'm getting the same numbers, except I'm not getting times 10 to the power of 14.
Oh, there's an issue with the scientific notation?
Yeah, I think so.
Okay.
So I don't feel like giving
Okay.
the wrong answer.
There's some disagreement about the numbers, guys?
Okay, so
My
that
calculator doesn't seem to want to show the 10 to the 14 though.
Okay, so this is a good process to go through then to see who's having troubles with the scientific notation. We'll
I
have
put
to
it all
iron
in
that out.
right, like we checked it.
Yeah.
And I put everything in right, but it's not giving the right number.
Okay, well, what are people getting? You had 10 to the 9?
I was getting 10 to the power 9.
You know, that's funny because I was getting 10 to the net power 9 earlier today too when I was doing this on my own.
I think I was getting it wrong.
Did
the whole time.
everybody get 10 to the 9?
Yeah.
for which the very
For the
Oh.
VV.
for all the energies.
Yeah.
Yeah, I got 10 to the 9 earlier too, and I assumed that I was making a mistake. Well, that's so embarrassing. Did everybody get 10 to the 9?
Yeah.
Well,
Yeah, I got 10 to the 9.
did you?
Yeah.
I was getting
Okay,
10
well,
to the
you know
9, so
what?
I just crossed out so much.
I think I'd like to go with a little bit of democracy then. I think it is 10 to the power of 9.
I'm pretty sure.
So that should be 10 to the power of 9. That should be 10 to the power of 9. That should be 10 to the power of 9. But now this should be what?
Different.
No, it should be the same numbers.
10? No.
It should be 7, I think.
Well,
Yeah, so the 7, because if it changed by 2,
Yeah.
it changed by
Yeah,
2
yeah,
again.
yeah.
So 10 to the power of 7.
yeah.
Okay, so that doesn't really change a lot. It's just going to change where the decimal place ends here.
Okay.
So let's try that one more time.
So-
We're adding a few extra minutes onto the video, but who cares?
So,
Yeah, I got 6.
What have we got?
623.141236.
623.14 1236. I mean, we're obviously going to round this off. Let's take it to 3 sig figs. With 623 meters per second, I mean, if the speed of sound hovers somewhere around 350 meters per second, I mean, we're going pretty fast, well beyond the sound barrier. And so if the fellow that was doing the Red Bull jump's goal was to reach the sound barrier, and he did this jump, overshot it tremendously. But the thing is, we don't have air resistance figured into this, so it might be closer to the sound barrier by the time it's all said and done, and we might actually get that sonic boom. But anyway, that's the math behind it. Neglecting air resistance, okay? So it's at least semi-topical. It's been in the news recently.